premier speaker. C'est l'heure. Hello everyone, and welcome to the NMRG session. So I'm Jérôme François. I'm co-chair of NMRG with Jefferson Campos-Nobre. To start the meeting, of course, let me remind you the note. Well, just to remind that IETF follows the IETF Intellectual Property Rights IPR disclosure rules. So it means that, here you have all the details and RFC, but basically if what you present will be covered, for example, by some patent, you have to disclose it. And just for information, today it will concern one presentation that has been our two disclosure for patent for the second presentation of today. And you can also look into that if you want into the IPR disclosure list that is on the data tracker. Sorry, wrong way. Also, what is important as reminding here is that the IETF is routinely make recording of online in-person meetings that includes audio, video, and photograph, and publish those recordings online. So, if you participate in person and choose not to wear a red "Do not photograph" lanyard, then you consent to appear in such recording. And of course, if you speak at microphone or appear on a panel or carry out an official duty as a member of IETF, then you consent also to appear in recording. And if you participate online and if you turn your camera or your microphone on, you also consent to appear in such recordings. Important is the privacy and code of conduct. So what is additional to what I said before is there are also privacy policies that you mentioned here and that you can consult. And important is also we agree all to work respectively with other participants, and in case of concern, you can contact the ombuds team. Although we have two RFC here, free RFC stories that you can consult for more details. No, just remind that NMRG is a research group, so it's part of the IETF, so Internet Research Task Force. It focuses on longer-term research issues related to the Internet, while the partner organizations, the IETF, focus on shorter-term issues of engineering and standard making. So the IETF is not a standard development organization. Still, in research group, we can publish informational or experimental RFCs. But yes, just to remind here, we have a research group of IETF, so more focusing on research collaboration and long-term issues. Okay, some links for today that you are, I think, most of all aware. What is important that we mentioned here is that the recording will be available on the YouTube, so you can easily find it as well. Of course, for the notes, although you can consult it after the meetings as well. So I will not take too much time because we have, as you can see here, a dense agenda. So we have different presentations. So I will just remind all the speakers really to also take care of the time that include question. We may be a bit strict on time as usual because we are a full session. So we'll put timer during your presentation, so please keep an eye on it. So thank you. I don't know, Jefferson, if you want to add something. Okay, so we can start with the first presentation. So Stefano, if you want to come to the stage. So the first presentation is Stefano Secchi about auto-supervised automation loop system for cloud native infrastructure.
Hello, everybody. Thank you, Jerome, for the invitation. Thank you, the co-chairs as well. So I will present you the result of some year of research we did at CNAM in Paris that has been taken over by a startup we have created, Neurotel AI. So it is about an automation loop for cloud-native infrastructure. So we have, let's say, defined our own way to implement the MAPE system to create a closed-loop automation of an infrastructure essentially composed of servers, containers, radio front-end, and I will present you today the result a little bit of this work. I will focus on the data pipeline system, which is there for the monitoring function, on the artificial intelligence functions, which is the core of the system, which performs anomaly detection, based on which we have a plan block which will take the anomaly fingerprint, and based on that, trigger the orchestrator, and this, of course, is an automation loop, so it will keep going. The principle is that, again, is the same we know since the MAPE system was conceived. We want to go from the current state to a better state, a desirable state, every time in which we determine that the current state is deviating a little bit from the nominal or desirable conditions. So the challenge is, therefore, to determine when the state is no more normal or nominal or desirable. And this is the first challenge, so to detect the anomaly, qualify that, and based on this qualification, determine how to get back to the desirable state. We want to do that in an auto, self-supervised way. That is, we do not want to use label, depend on labels and labeling processes. So let's, we start with the data pipeline system, which is a very important brick of the system. Basically, we are in a network infrastructure end-to-end. The reference use case is the 5G system, but it has been also tested with the IP multimedial cluster. The data pipeline system is there to bring a time series in real time from different possible data sources to the place or the places where this data can be exploited. So in the case of the 5G use case, it supports a number of endpoints, basically user equipment, containers, and servers running the RAN functions, disaggregated or not, and the 5G core. We use in our system a testbed, which is based on open source stacks, so Open5GS, but also Open Air Interface, Kudu, and other elements, as well as commercial elements. Just for you to really understand what we are talking about, as there are no public data set to test anomaly detection, reinforcement learning functions, we have built our own data set, we have published it, and to build this data set, we have built an end-to-end testbed where we have injected traffic from real traces from a specific region in France, and by replaying this traffic, we have monitored the infrastructure and extracted the states. The state of the different nodes are basically covering CPU, memory, input I/O storage, and the network matrix. The data set is made available. We are making different versions, so you can go in the first link to have a view on it. As it is pretty big, if you want to download it all, we will send a separate bulk link. And we are in the range of thousands of time series with a relatively high collection rate. We are in the order of 150 to 300 milliseconds for each of these thousands of time series. So this data is brought by a data pipeline system to artificial intelligence functions where we analyze it in real time. So this data streaming is done by a system that is basically a data pipeline system adapted from the IT world. where you have, the data warehousing system with data lakes and the related system. We simplified it a little bit. We took only what we think we need in this system. In particular, we have two brokering functions that, following a Kafka system, they get the data from data sources. They balance them to the following functions. In the middle, we have data processing, pre-processing functions that are there to basically perform matricial operations on the data, normalization, transform, and put things in order to the data for being processable by AI functions. So what do we mean with AI functions? We mean functions that can be distributed over the network or can also be centralized, to which we send this data in real time coming from multiple sources. So we are in the order here of thousands of sources if we think to an operator network, even hundreds of thousands for a large-scale nationwide operator, passing through these different data processing functions, so the input brokers that are able to balance and aggregate to data processing functions, which in turn can give the result of data processing to other egress brokers that in turn can do the load balancing toward one or multiple artificial intelligence functions. So let's have a look at these artificial intelligence functions that we named in a European project AIF. Again, we wanted to have a system that is auto-supervised, self-supervised, that doesn't need labeling. So in order to detect anomaly, we do not want to associate a given state of the infrastructure to a known anomaly, but we want to define freely what an anomaly is, give a fingerprint of the anomaly, and thanks to this fingerprint, let the automation system define how to recover that. So, and we are therefore using a relatively standard anomaly detection framework based on an encoder-decoder architecture, typically LSTM, but can be also other encoder-decoder architecture. The intuition is the same. We have an image of the infrastructure by means of these thousands of time series. We want to train the network so that the output will look like the input during the training phase. So this training is therefore done by minimizing the reconstruction error, so that given all the inputs, this reconstruction error over the training phase is minimized. Of course, the challenge is to give in the input the states that are really considered as normal. As there is no perfectly normal state, there is here a big challenge in determining how to select the input to train the network. And in the inference step, you go then checking the current state based on the trained network, and if the reconstruction error goes over a certain threshold, then you spot an anomaly. This threshold can be computed in a custom way. The way people typically do, it's based on statistical thresholds. So, for example, you could take the 99th percentile of the aggregate reconstruction error. As you can see, the reconstruction error here, the J, are the different metrics, or you can even group metrics among them so as to have a reconstruction error, which is the sort of average of the reconstruction error of the different groups. So that's relatively straight. The thing is that while we could live in a collaboration with Orange, because we had a PhD with Orange, while we could live with a single AIF for the IP multimedia subsystem, we could not do that while passing to the 5G system, which has much higher number of time series. So we went for a relatively classically here again federated learning based distribution of the artificial intelligence function, so that we can have edge IIFs to which we have to bring the data in real time, which are then training locally their own network, and based on this local training, they have aggregation with a centralized or semi-centralized. There can be multiple levels, servers that will then distribute the updates. These artificial intelligence functions can therefore be distributed. It has therefore an interface to get the data from the data pipelining, an interface to exchange the data potentially with the other artificial intelligence functions. In the case of federated learning, this data plane horizontal interface is not used, but is the control plane interface which is used to exchange the weights with the other AIFs, and then you have an outbound interface. So the nice thing here that we enjoyed a little bit to do is to model the fact that the management of the straggles, that is, you in order to have the highest possible quality learning, you need the data to come in a semi-synchronous way, in a synchronous or semi-synchronous federated learning. But if by chance the data arrives too late, then you may lose the occasion to use this data for the learning. So you have so-called stragglers. So we model the latency in this system as being the sum of the latency to get the data from the data sources, the latency to have the aggregation with the federated learning servers, as well as the training latency at the edge AIF. So you have an end-to-end latency which is mixing propagation delays, transmission delays, and the training delays. And of course, you would like to have this, the variance of this latency at the different edge AIFs, which is minimized. So how you can do that? By enabling AIFs in the right places, or by enabling on-demand hardware accelerator to accelerate the training latency when the propagation delay is too high, so that the training can be reduced. So this is a small game, as you can see, of balance between different delay components. And then, this AIF will end up by spotting anomalies. If you allow inference at the edge, you will also have the anomaly detection functions at the edge. Then when the anomaly is detected, you will require a way to characterize this anomaly, so a fingerprint, as I was saying. And thanks to this fingerprint, you will try to find a way to recover from this anomaly. So, and again, we want it to be self-supervised. So how you have to imagine this fingerprint as an array of reconstruction errors that can either be at the feature level, so thousands of reconstruction errors, so you have a big array, and that is the fingerprint. Some of these reconstruction errors will not be anomalous, but a subset of them, in case an anomaly is detected, will be above their own threshold. You can also aggregate these thousands of features at the resource level. So you could say that all the metrics related to CPU states, for example, in standard containers, CPU states are characterized by 50 to 100 different metrics, including temperature, page memory, faults, and so on and so forth. So you can also group by feature. This is what the theory suggests, that has been demonstrated in AI literature, that metrics that are strongly correlated with each other, better group them together and perform the encoding and decoding functions at this group level. So this is what we did. In fact, we grouped at the CPU memory network disk group, GNODB, and this part is not yet really developed, but we could also have a dedicated group to states related to user equipment or to other type of access networks, such as Wi-Fi access network. And you can have these at the container level, but also at the physical server level, so that you can monitor possible propagation. And in addition to this group, we also work to have a network function level specific metrics. So, for example, by integrating 3GPP KPIs for the 5G core. So, out of these, again, imagine big arrays, big or very big arrays of reconstruction errors that form the anomaly fingerprint. Each element of this array is a sort of dimension. So, you are navigating in what I try to represent here, a multi-dimensional space of points, infinite number of points, where an anomaly that you spot is one point in this multi-dimensional space. Here is, for example, you have only 3 dimensions, but in reality you have thousands. So that when you spot an anomaly, you are in a certain point in this multidimensional space, and of course your objective is to get back to the normal condition, to get back to the convex hull or the convex hulls, the different regions that you know to be normal. You know to be because you did the training against them, okay? So the challenge is, how can we work in this space and have a mechanism that is able to automatically find how to go back, knowing that how to go back implies applying actions such as scaling, rerouting, load balancing, bucket duplication, stuff like that, so that you go back to normal conditions. So this is a relatively natural field for reinforcement learning, deep reinforcement learning, and the like, where the actions can be defined in a dictionary of actions that you define, that you can, in fact, personalize based on the region where you are. So if you are, you suppose that you spot an anomaly that is in this multidimensional space extremely far away, and moreover is not close to any anomaly that you visited in the past, so we'll have really potentially a very long list of reconfiguration actions to perform. On the other way, if you spot an anomaly which is, from a Euclidean perspective, extremely close to an already known anomalies, seen anomalies, you may have the intuition that you could reuse the actions that you already used for that to mitigate that anomaly. Okay, so that you could compose a set of reconfiguration actions with a certain confidence on your capability to get back to normal conditions. So that's it. So it was a very synthetic way, but so I wanted to convey the intuitions behind this framework, which is currently based on this anomaly detector that I proposed to you, that gives the fingerprints of the anomalies to a deep reinforcement learning agent that has its logic to find the set of actions to implement in succession or by iteration. And we are currently thinking about replacing this anomaly detection and deep reinforcement learning block with a word model, which is supposed to get rid, potentially, of the reinforcement learning, so that you directly aspire the DPS, deep data pipeline system matrix live, and give as a result the actions immediately without the 2 steps, which are currently a bit challenging, not impossible to implement as we did, but which may be not extremely robust in case of very unstable states, fluctuations, state that change too fast, so for critical systems. That's it for today, if you have a question.
Thank you, Stefano. Any question? Yes, we have John. Please.
That's John from FutureWay. Question on slide 13, more or less for clarification. I understand that you're using a lot of network elements and data, but are you also using the UE data for this?
So for the moment, for the UE, I put it there because it's something we would like to do for some UEs, vehicular UEs in particular, where you have the hands-on the UEs, for vehicular UEs, for example, over the train or over the we are considering a European project also over the plane or the cars, where the UE is not a personal UE, but is an infrastructure UE. What we have anyway from the UE is the radio front-end matrix that, SRS and operating interface, they are exposing a number of KPIs on a UE level that we are collecting them, yes.
A closely related question, there's a function called NWDAF that's defined in 3GPP. Are you using any of those concepts in there, or this is completely separate from it?
NWDAF, right, that one, in the 3GPP 5G core, this is NWDAF, one, yeah. So network analytic functions is there natively meant and defined to process data that are coming from 5G core functions, so basically the KPIs defined by 3GPP. We go a little bit beyond that, even if also the NWDAF, as far as I know, I'm not really following 3GPP, but as far as I know, 3GPP is also thinking to extend the data scope of NWDAF to cover other data than KPIs from the 5G core functions. So there can be an overlap. There can be an overlap even if we are, again, scraping the data from the container level, so which goes beyond the KPIs of the 5G core functions, the physical servers, and also the radio front ends.
Thank you very much. Very interesting.
You're welcome.
Thank you, Stefano, again. And we move to the next speaker now. Where is my print? So next speaker is Peter. Just let me stop this one. Give you the floor. I have to stop first, I think. Stop it.
You can also directly share this. No,
No, you have to stop. Sorry, I'm just. It's here. Okay. Every time I look, I know I have to grant you. Should be okay. Yeah. Okay. Please.
All right, good morning, everyone. No, I think I'll keep it here. Thank you. Good morning, everyone. So nice to meet you all. My name is Peter Boers. I work at SURF, the Dutch National Research Education Network. And in my function, I'm the tech lead of the automation orchestration framework, and I was asked recently to come present here. So I'm very happy to be here. So first, a little bit about SURF. In case you are not aware, SURF is the Dutch National Research Education Network. We provide all sorts of IT services to higher education in the Netherlands. And the networking department that I work for is responsible for the fiber infrastructure and the layer 2, layer 3 services that we provide to our customers. All services on our network are fully orchestrated and automated, so they are there is no manual config. This is all done by our homegrown system. And yeah, if you think about our scale, so in the Netherlands we are quite large. The Netherlands is a small country, but for the Netherlands we are a large organization. We transport quite a lot of network traffic. And yeah, last year we transported about 1.6 exabytes of data, which is 392 million DVDs or 1.1 trillion floppy disks. And this picture I generated, but it gives you a good idea of why NRENs exist, because NRENs are in the world so that they enable science, so that they enable scientists to move data from their experiment to compute facilities. And yeah, if you imagine that people used to fly around the world with hard disks or floppy disks to move data, the reason why NRENs exist is so that that doesn't happen anymore. So, a bit about the work that we are doing in the area of intelligent networking. So, our ambition is to have an intelligent network capable of correctly assessing incidents and fixing them in real time with AI ops, right? So that's the bar that we've set for ourselves, and yeah, you know, that's a difficult problem. So and you need to break it down and try and figure out how you can achieve that. So AI ops, I'm sure you are aware of, but this is sort of our mental model. On one hand, you have data coming in, you observe that data, you do something with it with AI and machine learning, and then you can have a reconciliation loop that acts on the anomalies or the things that you detect. So in our stack, these are the basic building blocks. And today I'm going to talk about Sherlock and Clippy. I think that's sort of the building blocks that we have. And if you look at our stack and what that sort of looks like in practice, is that we have a telemetry pipeline that is ingesting around about 250,000 events per second from the network at a resolution of about 1 event per 15 seconds per sensor that we have defined. That gets sanitized through a streaming database, and eventually that sanitization narrows the amount of events down to a reasonable amount that you can process with an inferencing system. And that inferencing system is Sherlock. And then once that inferencing system has done its work and either detected an anomaly, yes or no, it will be passed on to Clippy, and Clippy will suggest something. And at the end of the day, that suggestion will either be approved by a human or not. And then our orchestration system will then pick up that and then remediate the problem. That's sort of the basic. That's sort of the basic principle. And you see here all the colors from the previous slide. You have the observing, you have the engaging, and then the action on the network. So yeah, defining the use case. So you need to start somewhere, right? And when we started 2 years ago, we decided to focus on highly disruptive events and incidents that are very visible in telemetry, but are not a binary event. So it's not up, down. It's something that you want to be able to detect that has a little bit more nuance. For us, because about 50% of our traffic is commodity internet, that was a very good use case to start with, because it is something that you can probably model quite well. Yeah, and this is our first iteration of this guy. So what we did is we defined a couple of sort of high-level goals that we wanted to achieve. And the first thing is that we wanted to have a system that is highly scalable, because we have quite a number of external peers that we need to model, that we need to monitor. It needed to be easy to train and easy to run. And we came up with the sort of the mental model of how you could look at an agent system that could model what the internet looks like from our perspective. So you can see that in the diagram. There's sort of like a VRF, then there's peers, and each peer has a number of neighbors, and each component would then have a machine learning model that would monitor that and help detect anomalies. This is our first iteration. Yeah. So what we also said is we wanted to evaluate a number of models, LSTM and transformers. Those two models, they could be useful, and they might be a good way to see if we can figure out if we can create something that can accurately model our network. Yeah, and basically, can we detect this? So this is a graph of a traffic with one of our peers, in this case Microsoft. And what you see here is that there's sort of like an anomaly that happened, and it existed for quite some time. Yeah, it was an inefficiency in the routing of our network, and we want to be able to detect this type of stuff. Right. So yeah, our first version took quite some time. I think about 90% of the time was basically an iteration exercise where we tried to figure out how we could deploy something in a production system where you have a battery of inference doing all sorts of stuff and trying to monitor all of our external connectivity. And if you look at the white diagram, you can sort of see what we came up with, because LSTM was the model of choice in our first version, is that we had a system which would sort of retrain our LSTM models every so often, deploy them inside of our data pipeline so they could do the inference, and then, yeah, we could detect anomalies, right? So you can see that as well, which sort of showed that the technology might actually work. And then, yeah, moving on. So these are sort of the results that we had on the LSTM model. And for those who are unaware of how LSTM works, basically the way it works, it tries to infer the next point. So the example here is the cat sat on the ... and it will know due to its training that it probably sat on the mat, right? And LSTM was reasonable, right? It worked well. Transformers, our first version, wasn't that good. And for Transformer, this is obviously the T in the ChatGPT, right? It works differently, is a different algorithm, and it knows the relation between different types of things that it sees, which intuitively sort of is something that's very interesting, because you might be able to leverage that if you want to correlate stuff between data points from a node. And Transform is also way more performant, right? So it is faster, it scales better, because you can create one model to rule them all, so to speak, instead of having a battery of LSTMs that you need to retrain every so often. Transformer is capable of being trained once, maybe fine-tuned every so often, in the order of maybe once or twice per year. Whereas LSTM, what we saw with the way that we did it was you can train it really, really fast, but you need to retrain it quite often. That's sort of the experience that we had. But as you can see from this diagram, our first iteration of Transformers was not that good. Yeah. So once we've done the integration exercise, and once we've sort of analyzed how stuff could work, we decided that Transformer was probably the way to go, but we needed to change the architecture of the model just slightly. And I have to really give credit to the people at our supercomputing center in the Netherlands who really helped me with this. We chose to move to inverted transformer, and our architecture changed quite significantly. So instead of having a streaming pipeline that would monitor every single event, and that process would do the inference at the same time, we sort of pivoted to an Oracle endpoint. So basically an HTTP endpoint that you can hit with a tuple, and then get an inference result. Yeah, and if you look at the model that we are running at this point in time, it's 100 million parameters, and these are sort of the vital statistics, and it's capable of inference, doing an inference with a step time of 15 seconds and predicting 32 steps ahead. And yeah, it takes about 4 hours to train on a very beefy GPU. And this is just a diagram. It's very difficult to see, but it's more to give the amount of rigor that we put into this effort. Is you can see all the training runs that we did, and the model that we actually selected is the one that sort of looks like this when you look at the loss over time. So on the y-axis, you can see the steps ahead that you can predict ahead. And obviously, step 0 is very easy to predict, and step 31 is a little bit more difficult to predict. And then, yeah, the bluer the tint is, the better performance that you get. And the loss after the 81 evaluation steps is around, well, 0.3, something that, or 0.35, that's something in that order of magnitude. And there's another graph showing the same, basically, where you can sort of see the loss over time, which, yeah, it does indicate that it trains well. At some point, it sort of stabilizes, and then but it does continue to to go down. Yeah. So deployment setup. This is basically the deployment setup. We have a stream processor that is able to sort of buffer everything and to make sure that we get data in order and on time. And every 15 seconds for every BGP neighbor that we have on our network, we do an inference post to that machine learning model. That telemetry is also stored, and the result of the inference step is also stored. And then we can visualize that in Grafana to see how our model performs. And these are sort of some of the graphs that we have. Also very difficult to see, but you can sort of see the inferred traffic. So that's interesting. Do we see traffic at the same at the performance that we expect? Inferred in, inferred out. But you can also sort of see the thresholds and whether it can detect an anomaly or yes or no. And you can see a small red bar. In this case, it detected an anomaly at a certain point in time. And whether this is a false positive, yes or no, we're still trying to figure this out. Whether we need to fine tune the model, yes or no. But you can sort of see it actually working, right? And yeah, this is very, very exciting step for us that it actually worked in production. But wait, can't you just use moving average, right? Especially if you're just looking at traffic. And well, yes, you could, but the thing is, due to the architecture, and especially if you look at the I-transformer architecture, you can see you have T is time, and A, B, C are sort of the different metrics that you are interested in. And as you can see with I-transformer, you get attention between different variables. That's very interesting because if you run this, then you can sort of start detecting anomalies that are that come across from different variables. So you can start detecting if things have influence on one metric or the other. And this is and it's also easy to scale, right? Because when you fine tune this model, you can easily add metric D, C, D, E, F, G, etc., without much effort. And you can start seeing attention across different metrics. So for us, even though it's in the first iteration, you just see, can we infer traffic? We also infer other things. It's just a thing that we in the plot that I showed, we just express the traffic. So our model is actually capable of inferring quite a lot of metrics at this point in time. So conclusions about the Sherlock architecture that can be extended, scalable, still needs some work, and it might actually be too good in the sense that it is able to detect patterns too easily. So you actually want a model that infers a little bit, that the inference is more stable, but it is actually able to infer. It's able to infer too easily in the sense that it changes its pattern too fast, and this probably due to the fact that in the training set there might be actually too many anomalies that it actually can follow. So rounding off, I think. What about Clippy? So Clippy is our other platform. Is co-funded by EU and the FNS. It's basically an agent-to-agent architecture that is capable of doing autonomous troubleshooting. And we've recently done a demo where we did that across domains, right? So we had our own agent-to-agent setup that was capable of talking to another agent-to-agent setup across the Atlantic with our partner organization, Internet2. And tying this all together, you can imagine that if we are able to get a machine learning pipeline and inference setup that is capable of flagging anomalies correctly, we can start an autonomous troubleshooting in this setup and maybe even get that running across domains. Yeah, there's a screenshot of that it actually worked. And I think I'm going to leave it at there. So this is our roadmap. And eventually we're probably going to rename Clippy to Watson. So, thank you very much.
Thank you, Peter. So we have time for a few questions.
Hey, this is Frank. Interesting work. How does the model that you trained compare to many other time series forecasting models like TimesFM, Moirai, Kronos, Cisco's time series foundational model, Toto, and the likes, right? So I think this is something that I think Nixler kicked off some 3 years ago to use transformers for predicting, and they're very good at that. We know that. So I just wonder how what you're doing compares to what the industry is doing.
Good question. So, to full disclosure, I'm not the guy choosing the algorithms, but I know we are going to be evaluating Toto in that sense. So, yeah,
It would be good
we haven't done that yet.
It would be good to run your model against public benchmarks in that space, right?
Yep.
So there's public benchmarks that are specifically done for benchmarking against networking cases. So it would be good to go and see that.
Yep. Thank you. Yep.
Hello, Thomas Graf speaking. Can you go to slide 11 briefly, where we see the network traffic and basically the routing change?
Slide 11. You have to help me. You have to say stop when you see it.
Okay.
I think
check
it's
out.
probably... this one.
Exactly.
Yeah.
So you were mentioning LSTM.
Yep.
How about seasonality?
Yeah. So the LSTM model had the notion. So we gave it some information about time and about time of day, day of the week.
Yeah.
The thing is, we needed to retrain it quite often to keep in touch with seasonality. So we had to retrain it every 2 weeks at least.
Okay. But you have like seasonal event, like we just had sports events like a couple of weeks ago. So where I'm going to is like here you have a routing event, right?
Yeah.
And I think you're looking at the BGP neighbor, if I'm not mistaken, right? Have you considered also taking other network events into considerations, like routing table changes? And
Yeah, sure. I mean, yes, obviously. It's just very difficult to deploy this at scale and get the streaming pipeline and the data integration set up. But yes, so I've showed all diagrams just about traffic, but there is much more in the model than just traffic, right? So yeah.
So just one recommendation, maybe have a look at BGP monitoring protocol, where you natively get that out.
Yes, we have
and
that.
also think about the transformations you're doing afterwards and taking basically the taxonomy and the relationships into consideration.
Yeah, I mean, I can't convey the complexity of the model, but yes, those things are in there. Yeah.
Definitely interesting work. Thanks.
Yeah, thank you. Yeah.
Just two questions. One is quite simple. That you are not using the data sets are not labeled, right?
The data sets are not?
Are not labeled, are not associated with a particular event or a particular. You mentioned that you are considering going for labeled data sets is for further work, right?
Yeah, so the data sets is it's just streaming telemetry and some syslog, and BMP information is in there. That's sort of about it.
And the second is just an idea, probably more for the, I don't know, for the giant project. Have you considered to use this as some kind of emulator of a BGP neighbor just to?
Yeah, so the goal is that once we have this set up, that we should be able to have a model if we add more layers and more complexity, that is capable of being sort of like a digital twin. That's the ambition.
No, exactly. Well, it's,
Yeah.
when you have something like that, it would be very good that you come here to tell us anyway.
Yeah, thank you.
Just a last question, Leandro.
Well, one, after I will look for you. How often do you retain this model? For a year?
So we have 2.5 years of data. And at this point in time, we've trained it on 4 months of data, and we haven't had to retrain it yet. We expect that we have to retrain it once every so often, but we're not sure yet. We've just deployed this a couple months ago, and it's still running fine. So we haven't had to retrain it yet.
And the time to train is about
4 hours on
4
a
hours. Oh,
yeah, 4 hours on an H100. So you know, you need some serious
for each
infrastructure.
peer.
So
For each peer.
yeah, it's just the whole network.
Okay.
So we take data from the whole network, we put it into a model, it runs for 4 hours, and then we get this and we can deploy it. And you don't need so we do need, because the amount of events coming in per second, we do need a GPU for the inference, but you just need a tiny GPU. It doesn't need to be anything special. Yep.
Thank you.
Thank you. All right.
Thank you again. So let's move to the next presenter. So Christopher Jans. So we have 3 presentations. Let me stop this one. Okay.
Okay, I'll try not to make you listen to me for 30 whole minutes. The third one will be quite quick. We might spend a little more time on the first. This represents content from 2 later breaking drafts that I started the ideas with Nigel and Diego last year. And some of the later breaking stuff in this companion draft is based on conversation with Brad Peters, having looked at the first. So I want to run you through the ideas. Is there a clicker?
Sorry.
Thank you.
Just a second. Yes, sure.
Doesn't matter. Okay. So the context here is, okay, we love to do Yang models in IETF. Why do we do them? Because when 2 systems want to talk or understand information, let's say communicate, they need an unambiguous basis on which to do so. So they need to agree on what entities are part of the universe they're going to talk about. They need to agree on what they're going to be called, how ideas are represented, and then a sort of grammar, right? You get all 3 by fixing a data model. But of course, human beings don't require this sort of agreement in advance, right? They can work it out on the fly. If you go back to the Bronze Age, a Phoenician trader could land on an Egyptian port and they could figure out how to work out a deal to sell copper, right? So this tells you a few things. One is that why are we endlessly generating Yang models? One of the reasons is that they're brittle in a sense. They're very conversational purpose specific, right? By definition, you never have the right ontology for every conversation unless it's an unlimited one, et cetera, right? So the idea is when we have cognitive AI, cognitive agents that can, in principle, communicate intelligently, reason, plan, and learn, can we approach things differently? You still need unambiguous interpretation of communications, the semantics. But can they work it out more for themselves? And does that have implications for the data structures that are worth standardizing or that serve as references? So the general context here, and there's many detailed use cases you could work out around the theme, but the basic idea is we have 2 systems that want to communicate and they're both cognitive. Something on, in the structure of this, I want to focus on lexicon, which is really a piece of an ontology. It's what the entities you're going to refer to are called, or attributes or predicates, etc. But it's basically nomenclature, which is a subset of ontology. A data model is all of that in a specific sense, represented in a specific grammar, right? So we're going to sort of, what we've discovered is that the thing that's really important here is actually lexicon, because it's where you need to start a mediation, a reconciliation process. It's where most of the work goes. The rest is a little bit easier if you get that right. And it kind of suggests that almost from the start that reference lexicons rather than reference ontologies, which are more flexible than data models, but still they're specific, right? So they're less, lexicon is far thinner and less brittle than either of those two. But you want to think about it as potentially more than just names, right? And there's some, what's going to assist in disambiguation. So in the flow of the demo here, it's, again, many possible use cases. This one is two agents that are, they're using different data models which happen to be standard defined. And they want to talk to each other and agree on how to translate between the two, right, with no humans involved in that process. So think of it as like an automated system integration task. So first of all, they're passing messages over an A2A bus. They agree on a process, right? And the process they agree on is basically we're going to sort of lift our data models to ontologies. We're going to sort of try and map or represent the lexica that those represent. We're going to agree on those. After that, we can identify ontological gaps in detail, abstraction or granularity, for example, in scope, what is within or not within a specific ontology. You can add to the one that has the deficient ontology. And then, how are differences in grammar, if you like structure, represented ontologically. And they do this by conversation, right? So starting with, okay, let's look at the lexicon, let's try and do simple matching, recognizing this isn't done, you can get false cognates, but you get a good starting point. Then you've got to do another pass, which starts to draw on other information, what this is calling the gloss, which is that sort of explicative, ampliative, disambiguation supporting information that you can draw on, and eventually you get through the process. Having done that, you've already got a good handle on where the detail and scope gaps may also lie. And we found that the machines are actually very good at sorting through those on their own. And in this process, what you end up with is, first of all, you've done this sort of generated translation artifacts for the data schema. Then you can get onto the specific instance naming and things like that, right? When you have specific knowledge graphs and not just generic ontologies. We agree on what a table is, but I want to know that I call that table 1, and when you call it table 7, you're referring to the same thing. But there's a process for that works. And eventually you can sort of validate the artifacts, right? Depending on the problem, you may be able to do things like, hey, if I want to push a change to the network, I represent that in my data model. It has to go through a full round trip double translation, so I'm satisfied I get the same artifact back. I know we're both going to do the same thing, for example. If you can have reference lexica, or at least having done some of this heavy lifting, post to the public domain some of these reconciliations of reference lexica, you've taken out a lot of the work. And this becomes a lot more scalable when more systems are trying to do this. The implication of all this is, I think we validated, and ours is not the only work, this is an active field, that cognitive agents can work out a lot of things in order to communicate and represent information unambiguously, much more flexibly and with much less sort of human created or standard support than we are used to in the past with non-cognitive systems. The go forward topic we're looking at is, how to support this, okay? If you can sort of step away, and maybe you don't step away from, Yang data models entirely. They're excellent references. Depending on the case, you may need to build from them. But, if it's Lexica, which is the more flexible tool, but it's not just a simple lexicon, what are the things you would need to augment it with in order to serve in this kind of environment as referenceable objects, while minimizing the scope for problems or the cognition workload in reaching agreement, right? And there's some examples here. Okay, that's it for that one.
You want to take a question now?
I can, yeah, sure. Any questions?
Hi, Kent Watson. When you're talking about agent to agent, I mean, it makes it sound more like peer-to-peer, but most of the time I hear about agent to agent, it's more like, top down, like the orchestrator talking to a controller, controller talking to the elements. So it's more like the scope of, the control.
Well, I mean, we've taken it simply as a protocol for communication between two agents, regardless of their
Well, I mean, you talked about table 1, I call it table 1, you call it table 7. What's the actual practical network application of that example?
Well, in this case, we have two distinct, we have different data models on each side. There's a different data model schema.
Who's we?
I'm sorry?
Who is we in your example?
Okay, well, sorry, I thought I explained the use case, but we have one network, we have two independent agents, which are using two different data models to represent that network for configuration or other purposes, right? And they want to be able to talk to each other, right? Or whether, yeah, sorry, Diego, maybe you want to intervene.
Just to try to provide an example from the some experiments that we have running. Think about a public network operator and a private network in a corporation, and that they have something, some smart stuff there that has to communicate, and not necessarily are sharing the same ontology, and they're not the same. And these are more peer-to-peer relationship. For sure, the public network operator would be typically bigger, but at the end, you have to put it. This is one thing. The other thing is within organizations like mine, in which people that are running the radio don't talk very often to the people who are running the fiber, for example. That's another case.
Yeah, I mean, I think like a lot of AI things, we're looking to automate things that currently have to involve people because they involve planning, judgment, learning, right? We now have technologies that can do that. How can we apply them in some of these situations where we've had to rely heavily on standards to define information or data models, content structures? That's the general problem statement. Okay, the next topic, a little bit different. This one was motivated by a discussion, some participants in ETSI's ESM, where topics of closed loop and intent conflicts and their coordination got a lot of attention. It's also a very active research field, and we connected with some people doing research in that area. It was motivated by an NMOP draft that I'll refer to at the end. But it's so this is basically a survey of a complex, what we know about this topic, because there are things, it's a bigger topic than you might think, more complex and potentially difficult, an important topic than you might think. And it may have implications when we think about network management architectures with agents in them, beside them, around them, on top of them, whatever it is. The main thing to understand is that because the whole point of agents is that they're supposed to act independently, the decisions they take and ultimately the actions they try to drive can conflict with one another. So what do you do about that? If they're just sort of generating information that, it's information, then you don't have to worry about that. But if that information is leading to action decisions, then you do have to worry about it, right? Then you have an issue. And The conflicts and coordination, that is how you detect, preempt, or resolve those conflicts, are flip sides of the same coin. Again, it's not, an agent which merely generates some information to be digested by something is not going to be a problem. An agent which tries to drive action is something you need to pay attention to, because it's at the actions or the decisions leading to the action that the conflicts arise. And there's a whole bunch of different types of them, right? Some are hard. That is, you ask me to do this, something else asks me to do this, and the two are in hard conflict. More often they are soft. That is, you want a lot of bandwidth, but you want it cheaply. Well, those don't tend to go in the same direction, but whether it's an actual conflict is a matter of degree and circumstance. Action ordering and impact, right? I mean, two things, actions that look independent, but once you get the result of both, or maybe dependent on the order in which they happened, you've got a result that neither liked or something else didn't like, etc. Right? And a characteristic under this is that only a small subset of conflicts are detectable on inspection. Mostly they are emergent, which means that they only appear when you try to come up with solutions that satisfy all of them, right? So basically it's in the collective decision action of a bunch of different agents that you see that there is conflict. Right? So you can't rely on things like, oh, in my workflow, I did intent inspection and I resolved all my conflicts, because that's not where you're going to catch most of them. We've identified 10 families of coordination mechanisms that are out there in the application and research field. And to some degree, they depend on two things, really, their applicability. Are the decision and action loci within essentially a common place where you can link them, evaluate them simultaneously? That, and are they under some kind of coordinated or similar authority, or are they really independent and sovereign, right? According to those two axes, you have different methods that can help you. For example, you may in some cases simply have scope for imperative arbitration or normative regulation. On a very decentralized kind of sovereign agent thing, which may conflict on use of resources, you're going to need to rely on something like markets, right? There is no centralized coordinating aspect. In the middle, and if you're putting all your nominally independent network management agents within the same structure, then you can use this family of structured reconciliation kind of methods, whether that's a joint utility kind of calculation and optimization, some kind of negotiation, some kind of, there's a big family of distributed constraint optimization processes that you can use. But, it gets to this point that the architecture of distribution of agents says a lot about what kind of conflicts and how you may be able to resolve them. I should say that cross-cutting, there's this notion of if you can use something like a digital twin to look at, okay, I'm going to do everything all these guys want to do. What have I got, right? That's kind of a general fail-safe. That can get you at that's not only a technique you can use within the structured reconciliation cluster, but it's also the only way you're going to get at things like order and impact conflict detection. So you want to conceive of a structure that's got, multiple pieces. A digital twin is probably going to play a big role generally as an exploratory leg before commit and a diagnostic post commit. You want to look at, hopefully a lot of your agents are within the same network management structure. You can coordinate decisions and use techniques that are suitable to that. The NMA draft is one we were pointing to, and of course it allowed for many permutations of where the agents could be placed, which is what tweaked this in the first place. The kind of advice is not adopt the NMA inside MD, but focus on that first, because that's kind of the natural mode. There's, it's much easier to deal with conflict detection, resolution, preemption in that sphere. Again, there are some that, you're going to have agents outside the actual, what they call controller, what I, as more of a ZSM guy, might call a management domain, but there you go. So this should be thought through because it has implications on architecture, and potentially, if we're defining interface models, are there communications related to coordination that need to figure in? This may be, something that can be deferred, but I think eventually should be brought in. Okay, that's it for that one.
Thank you. I think Alex is in the queue. So I don't know if it was for the previous presentation or this one.
Okay.
Alex, we cannot hear you if you...
Oh, sorry. Can you hear me now?
Yep, perfect.
Okay, sorry. Yeah. So this was actually for the previous presentation. If I can ask this now. So I think this is actually a super interesting set of presentations. On the earlier one, I would have the questions now regarding the reconciling the models and so forth. It seems that a lot of this is concerned with when you want to read or observe or monitor information. So basically, perhaps assurance type of operation. But since Yang models were mentioned specifically, there are also constraints that are sometimes expressed, right? You have constraints, you have conditions, you have dependencies and so forth. Do your techniques, or are you also considering those? Have you looked at them? Do they matter, or are you looking basically first at some functions before you tackle those types of problems?
Probably for now, I'll just say it's very early days. We picked a case to try, which is kind of an obvious one, a bit of a workhorse, just to see what a workable process flow might look like and where whether there's prospect of success. Can the agents do enough thinking and learning to sort of bridge gaps? Is there a basis to continue? There seems to be, but it's very early days. So I'd love to talk to you offline, or anyone else who's interested in this problem. Obviously, there were various flavors of this manifested in different contributions and different side meetings. This week there was a side meeting on Yang modeling in the AI age, or for AI systems, which touched on some of the same general grounds. So I think there's definitely the scope to do something different in an AI agentic world. So, but it's very early days. So, for specific questions, let's maybe talk offline, if that's okay.
Okay, cool. Thank you.
Okay, this last one I'll do fairly quickly. I don't want to overstate my welcome, and the key points can be made very easily. Okay, so this one is saying, we talk a lot about performance on demand and dynamic networking requirements, and we're trying to create an automated, smart operation system that can take intent, can take a changing intent, can do service assurance, and can cope with these kind of dynamics. And we sort of neglect the problem of, well, we assume that a service intent is coming into the system, but how is it coming into the system, and from whom, and why, right? In a fully automated dynamic environment, you can conceive of agents on the demand generation side, not just the BSS, but the end service user, something that's saying, look, I'm an AI environment, or this other cloud computing environment, and I have dynamic distributed workloads, and I want to, I manage that, and I want to be able to pilot my network services dynamically, directly. Now you've got an agent-to-agent conversation flow that bridges not only the consumer-provider boundaries, but does that potentially in a commercial context, right, where you've got a service provider and a service purchaser. And this isn't completely addressed. What we wanted to show here is that we actually don't need any more models to do this. There's only one sort of new piece in the agent ecosystem that's necessary to automate this, and actually you all know what it is. Just the basic situation, you've got some enterprise or other customer system which is piloting its dynamic networking requirements. It knows why it needs them, etc. On the other side, you've got a network system which is able to provide those, but in a smart way. It's able to dynamically plan for services. It's able to assure them once committed. It's able to yield information that may be relevant to pricing, like resource scarcity information. The BSS is what connects them. You want that to be intent negotiation across the board. And here in IETF, we tend to talk about intent strictly as a data model. In other places, it's also talked about as a process flow, right, where there is a negotiation to get to the agreed intent. So we invoke some of that from TM Forum and Etsy. The missing piece is, the BSS is really central here because it's the thing that basically gates the completion of a negotiation and the actuation. That sort of concludes the contract. But for that, there has to be sort of established agreement to the terms on the part of the customer. And the way that's done generally is with a digital wallet, right? Something that says, hey, for this purpose, for these purposes, these are my priorities, these are my spending envelopes, etc. If you're within those rules, which I can update, but those rules are your guidance, right, when you're negotiating. So, I'll skip over the use case example and demo that's in the contribution and skip right to the end. The bottom line is that, again, at IETF, we think a lot about models, but sometimes process is the completion to the solution rather than a new model. So in fact, we have all the models we need from different organizations to make this happen, including the agentic or digital wallet piece. So we're definitely using the service and then in the OSS, the other network, etc. models that have been developed in IETF. But for the negotiation processes and some of these other surroundings, we're using elements from elsewhere. And what we found is there's nothing missing. So it may be a useful lesson as there's more attention in some of the IETF groups on, hey, we want to do these kind of dynamic. I heard this discussion this week. If we want to support these kind of dynamic services, do we need a new Yang model that allows us to define the parameters of the dynamics? Well, our contention is no. It's don't solve it with a model. You have a model which can define the service you need at any point. The point is you've got to agree on what you're executing, and if you change your mind or have new demands, you're presenting that as a separate request. So it's a process overlay, not a requirement for a new model. Okay, that's it. Love to have any feedback on that.
Thank you, Chris. Feedback or question? Okay, I have one, okay. Which is more general comment and feedback, because you present a lot of interesting stuff and a lot of questions and problems that needs to be solved. I was wondering actually two questions. The first one is what your expectation from the NMRG on this question. Do you want to ask for some support, for some help in some of this question? And the second one is more about the question in general that you would like to address. For example, if you think about as you mentioned, actually, about the conflict, addressing conflict in agentic AI with different actions is something that is not specific to our domain. And I don't know how you also look into the other domain, into the AI community as well.
Yeah, and I don't think there's one answer. I mean, as I said on the first topic, it's clear that there's some forming sense that there is an interesting macro topic there. There's discussion this morning about, will we have a new AI ops group? If so, what kind of agenda? Some colleagues ran a side meeting on Wednesday that touched on these aspects. So it's forming, but clearly there's agreement, there are some possibilities. They're worth exploring. It's not clear where in the organization the focal point might be. But I thought I'd introduce it here because we are a research group. For the moment, it's a research presentation. But certainly, if you're interested, I'll make sure that the conversation around this is on the AI Ops mailing list. It's probably a good focal point, and you can jump in and we can work. Probably a next step is, how do we get to a topic either within a working group or something that's focused on this area, and then we can get sharp about what we're trying to solve. On the second one, I think it's more when certain things are happening around agents, there's now a group of people that are cognizant of some things that need to be paid attention to and potentially leveraged. And again, if you're looking for interesting research problems, it's a very good area from what I'm seeing. The third one is more like, I think it's just a lesson that, Yang models may be our hammer, but that doesn't make everything a nail, right? A new model is not necessarily the solution to every problem. This was a case where, a desirable utility scenario was fulfilled by working on process over top of existing models, but key models that are not only from IETF, but that are composed from different parts of the ecosystem. So.
Okay.
All right.
Yes, I think, Laurent, if you have a quick question. Quick. Quick answer.
Do you want a joke also or not? Because it's not a question about quick, it's a question about presentation. Okay, it's more about the second presentation you had. You were describing a number of coordination patterns, and I think some of them are already kind of solved or addressed. What, from your point of view, will be remains open for research in terms of coordination mechanism or discovery? What will be a bit like where to look into?
Yeah, so I mean, we got connected with people who are, for example, discovering the limits of the coordinated approaches like DCOP and utility, and looking at the mechanics of market-based methods, even within domains that you wouldn't think you need to use them, or they're not natural. There's a lot of, these guys are doing some really hard math to sort of sketch the boundaries of utility and methods, et cetera. So there is definitely, and then even within the known methods, I think their application is not necessarily straightforward. So I think there's a lot to become expert on, a lot of research going on. People that can apply that to our systems. I think, the reason we brought it up here, thought it was worth doing, is just that, people are conceiving of nominally independent agents and architectures, and there are real implications they should be aware of. And we at least need to think through how that might bound the architectures we recommend. And if we're developing augmentations to protocols for their communication, is there something related to coordination that we need to anticipate? The answer may be no. It may be just another generic field you can undefined field you can carry, but maybe. Anyways, we thought it was interesting just to bring forward.
Thanks a lot.
Thank you. So next speaker. Okay, I think Tarles, you are the next one. Alex will present. Okay.
Hello, can you hear me?
Yes, perfect. To just put your
Okay.
slide.
Okay. All right. So, hello everybody. Basically this is a fairly new draft that I'm presenting on agentic AI for intent-based networking. This is the outcome actually of a series of discussions that Turles and I have had over for a while, and we decided it would be worthwhile actually to capture this and in this draft and present this here. Let me see, how do I advance the slide? I guess here. All right. So basically, this follows up on RFC 9315. Basically, this is where the intent-based networking concepts and definitions were defined, where, of course, intent being the set of operational goals that the network should meet and outcomes that the network is supposed to deliver, would be defined in a declarative manner without specifying how to achieve or to implement them. And of course, this sounds a lot of what also agentic AI and so forth, and large language models and so forth seem to be enabling. And so, given the recent explosion of these, the question is basically, does it make sense to revisit some of those questions, or basically see how can we leverage this to move closer to intent-based network, which and particularly also, for instance, which functions in intent-based networking stand to benefit, and also are there any updates and so forth needed? And a similar question actually pertain also to autonomic networking. So basically here, autonomic networking as defined in ANIMA and IBN kind of like work hand in hand. And there is actually a companion draft also championed by Turles in the ANIMA working group. And one way in which they go together is always, well, intent is recognized as a necessary component of autonomic networks to provide guidance. So just as a reminder, so basically the draft is cycled or basically structured around the life cycle and reference architecture that we have in 9315, which basically lists a number of functions and so forth, how they tie in with each other. And now basically in discussing the role of agentic AI with this, we can basically look at each of those and their interaction and see basically how they might apply. And so basically looking at some of them, actually the first ones, particularly the translation refinement step, that seems actually a very natural fit for agentic AI. I think Christopher's presentations just prior to this actually are very indicative and actually very relevant for this space as well. And likewise, basically, the whole aspect then of orchestrating intent seems to be a natural fit for agentic AI planning capabilities. There are various functions that can benefit from those that we are outlining basically in the draft. Basically, as a general rule, I guess, the leverage agentic AI translation capabilities make it also easier to mask interface heterogeneity, which simplifies, of course, some of the biggest headaches in network management always have to do with dealing with differences, variations in models and so forth. Actually, again, tying in very nicely to the presentation that Christopher just gave. However, there are a number of gaps that are clearly also recognized. For instance, when it comes to not just translating and rendering steps, but we're actually developing smarter strategies to optimize networks, as well as dealing with rainy day scenarios, where basically we need to, for intent-based networking to be effective, you really need to have the network to stay in character and allow the operator to interact with it just in terms of intent, not by reverting to, for instance, to need to know or deal with very low-level device parameter settings, for instance. And then finally, of course, there's a whole assurance part of the loop, where again, abstraction and reporting agentic AI strengths that can be leveraged in various ways. There are also some severe practical limitations still, and I think one thing to point out there specifically concerns the data velocity. Simply, basically, the if you want to do this in real time, the amount of data that comes through events, through syslogs, through telemetry, through other data streams and so forth, can be expected to overwhelm the ability of LLM infrastructure, token processing capability for the near future without any ways to deal with this. So basically, with this, the questions are here also why we're presenting here in NMRG is basically, first the question is basically, is this a discussion that is worthwhile having in NMRG? Basically, the question is also how can NMRG contribute shaping this space? Basically, the way we see it, this is actually a very fast-moving area, and a lot of the stuff in agentic AI is happening kind of like with or without IETF. And the question is basically, and products will be also can be expected to emerge, but the question is, what role can we still play and help us to shape the discussion? Likewise, basically, how do we, should we pursue this draft further and refine it further? There is a lot of other work also that is here, but kind of like is all a little bit unstructured and the connection is missing. And of course, they all look at slightly different aspects of things. And anyways, this is a starting conversation starter, if you will. We're looking for collaborators. Please contact us. Turles is also in the room. I'm remote, but both of us on email. And that concludes what I have to say.
Thank you, Alex. We do not have so much time now for questions because we're a bit running out of time. But of course, I will encourage people to go on mailing lists or contact you. Just a quick comment from my side and personally, but also on chair. So we of course identified that with this AI era, IBM clearly is a topic that is worth to consider in general in the sphere of research in network management. And that's why I think it was in Montreal, we organized a kind of session around this topic, somehow again to revisit this with ISO. Yes, probably we continue to investigate, or we can also continue on this in an NMRG, of course, depending on the support you have. But yeah, thank you for the presentation.
Can I just make just a quick comment, right? So collaboration, for example, if you have examples of pieces of that solution where you already are using AI, right? So those things would be very nice to capture in the document as well, just to understand the current state, not generically, but also by practical example.
No, sure. Okay, thank you. So next presentation. This one's okay. Yes, the next presentation is from Xiangyu.
Yes.
Okay, thank you.
Good morning, everyone. I'm Xiangyu from Tsinghua University and Zhongguancun Laboratory. Today, I will introduce our new draft, which is Intelligent Data Plane.
Not speaking on the microphone, please.
Okay. And our goal is to make the intelligent processing in the data plane and safe and manageable. How to change the page? It should be okay now. Okay. So the network data plane is changing quickly, and in the past, the data plane is merely forwarded packets, but today the programmable devices can collect information from the traffic and analyze traffic at line rate. This creates new opportunities for AI-based network management. Our previous research shown on the right has demonstrated that such processing is possible. However, these systems use different interfaces and data formats. They also face similar problems with resources, state, and security. IDP builds on this research and provides a common framework for addressing these problems. So what do we mean by IDP? IDP processing has 3 important properties. First, it must be bounded. In other words, it cannot use unlimited time and resources. It must also use follow network policy. A decision function can only perform an authorized action. Finally, it must be observable. The operator should be able to see what is happening. The process itself is simple. The node collects the signals and extracts features. It then runs a decision function and produces a result. If this process fails, the node enters safe mode and continues basic forwarding. The basic process gives us the architecture shown here. The processing path moves from the signals to features and then to result to the decision and finally to an action. We identify 3 interfaces. The northbound connect the IDP nodes with the network management systems, and the east-west interfaces connect the different IDP nodes. And finally, the internal interfaces will connect the forwarding engine to accelerator. These are logical interfaces, and we are not proposing 3 new protocols. Across these interfaces, IDP use 3 types of informations to communications with these systems. The first one is signal, and the second one is features, and the last one is results. The signals describe what is happening in the network. They may come from the packets, the flows, and the devices. The nodes use these signals to calculate features, and a decision function then uses these features to produce a result. The result may show a traffic class, an anomaly, or a confidence value. 2 rules are important here. A result is normally only a hint. Network policy decides whether it can affect forwarding. Also, old information should not be used for a new forwarding decision. The decision function does not have to use a specific AI algorithm. We describe its processing in 3 steps. The first one is partition, which divides the input into smaller parts. And the second one is map, process each part. And finally, sum reduce combines these results. Because this model is general, it can be implemented on different hardware. A switch may use tables, while an FPGA or SmartNIC may perform a more complex processing. In every case, the decision function must have a clear identity and version. The node must also know how many resources it needs. These functions also need to communicate with other parts of the system. Through the northbound interface, the node reports its capability, and the managed system can then install the suitable policy. Through the east-west interface, IDP nodes can share information or transfer a task. Through the internal interface, the forwarding engine sends a work to an accelerator and receives the result. Existing protocols can support this interaction, and our communication must remain within the policy and trace the scope of the IDP domain. Not all processing needs to happen in the same plan. Simple and time-sensitive decisions will be deployed on the fast path, and more difficult cases can be sent to an accelerator or an external system. We call this escalation. For example, if the local result has low confidence, the node may request a more detailed analysis. However, escalation must be controlled in a maximum rate and a timeout. Another protocol issue is memory. The IDP functions need to remember information about a flow. However, forwarding devices have limited memory. The node therefore needs clear rules for managing this state. IDP may also use existing mechanisms to carry metadata. This draft doesn't define a new metadata format. Future work must explain how the information is protected and what happens when a node does not understand it. These design choices are summarized in 24 requirements. For clarity, we organize them into 5 areas. The first 2 areas is input and the decision function. And the second, the next 2 cover communication and the state management. The final area covers the security and privacy. Across all 5 areas, the main principle is the same. An IDP function must stay within its resource and policy limits. Security is especially important because an IDP result may change how traffic is handled. For example, an attacker may provide false signals or install a harmful model. An attacker may also try to use too many resources. The node must therefore check the source and the integrity of important information. A decision function must never bypass network policy. IDP must also protect privacy, even without reading the packet content. Traffic patterns may reveal sensitive information. IDP is not intended to replace existing network mechanisms, and existing work supports network management, memory, traffic steering, and data export. At this stage, the document is just a framework. It doesn't define a new packet header or a new protocol. Specific protocol mappings can be developed later. So that's all. Thank you. Any questions?
Thank you. Unfortunately, we cannot take questions now for lack of time, but yeah, I just encourage people to ask questions on mailing lists or in the chat. But thank you for your presentation.
Okay, thank you.
Thanks. So next one is Shailesh. I'm sorry, we have to reduce a bit the time for the presentation. Sure.
Yeah. Hi, this is Shailesh from Nokia. I'm going to introduce a framework on normalizing multi-vendor network inputs for LLM-assisted network management. So over the past year, we have seen tremendous efforts in integrating LLMs into network management operations, and even in the context of IETF and IRTF, we have seen many drafts that have been working on MCP, A2A, and LLMs integrating into the network management systems, right? So one of the key challenges that we're going to face is the multi-vendor network elements are going to represent the same data in semantically different languages, right? And when this data reaches the LLMs as prompts, because of the nuances in the representation, there is a risk of misinterpretation by the LLM, which can lead to the mismanagement of the network, right? So just to quote an example, say vendor A can say show interface, vendor B can say display interfaces, right? And vendor C can say interface brief. So all of them are the same intent, but they differ in syntax, terminology, field names, and hierarchy, right? So here's the current workflow, right? So there's vendor specific data. It could be alarms, telemetry, configuration messages, operational response, anything, right? So because they're vendor specific, there are vendor specific ways of prompt design and parsing, right? That is fed into the LLM, right? And because the prompts and parsing logic was vendor specific, then we have AI applications that tend to be more on the vendor specific side as well, right? So this limits a lot of things, that including portability, interoperability, scalability, and prompt reuse, right? So here is the proposed frameworks, right? So what I propose is an input normalization layer that sits in between the network multi-vendor network elements and the central LLM that is managing the network, right? So it starts with an input classifier, which is essentially a small language model, right? Which helps us classify whether the data is performance data or a configuration data or an operational response, right? And based on that, it is fed into the prompt schema generator. So the schema is not restricted to a specific format. It could be JSON, it could be XML or YAML structures, right? So, and finally, the schema, the standardized schema is then fed into the LLM for further processing, right? So this way we receive consistent inputs to the LLM as prompts, which helps us in common abstraction and better interpretation and better management of networks as a result. So, feedback requested, right? So I would like the working group, the research group to let me know if this is in the interest of, is there interest in pursuing this problem within NMRG? And I'd request the chairs also to, kind of consider this problem within the research group, right? And I'm also looking for volunteers to review the draft and let me know if any, deployment scenario should be considered, or, if there's gap that we need to fill in the draft, right? Yeah. Questions?
Thank you. You are very effective, so you have time for questions. We still have 3 minutes for questions or feedback. Yes, Laurent.
Hey, so I think it's interesting work, and there are some discussion, especially in this IETF meeting, about agent ops, AI ops,
right.
Monitoring. I think this could be an interesting contribution because it's kind of a normalization function that can sit between different agents that needs to communicate, or an agent and a networking management system, or even other functionality. So I think this could be an interesting work to push into different discussion area. I'm not sure where it stands into the network management research, but network management, definitely.
Yeah, thank you.
Roberta?
Hi folks, Roberta here. Just to say that I really like this idea and this approach of having something that might be neutral to, to companies and might, fit things properly inside of the schemas. And I'm really looking forward to be able to contribute and to review this work as well. Count on me. I'll talk with you later.
Yeah, thank you so much.
Just very quick, Chris Huawei, what you're talking about here is not at all orthogonal to the first topic I presented. I mean, it's part and parcel of the general theme. And as I said, there's many manifestations or particular use cases or instances of that theme. There have been quite a few here. There was a dedicated side meeting swirling around it. So I'll make sure, as I said, I think that we'll figure out somewhere through the AI ops mailing list and that process, somewhere where work on that theme should be done.
Yeah.
And exactly, what points to. So I'll make sure you're on that mailing list.
Sure. Yeah.
Apart from what Chris has said, that I believe that there is a very close relationship on what he was presenting about the different ontology fields and this, because at the end we are trying to reconcile ontologies or well, at least the semantic fields and not. The point is that I think there is, apart from identifying ways for standardization, there is an interesting matter here, I would say, in terms of research, that is precisely evaluating which are the most suitable techniques to be applied. The architecture, I mean, the architecture you have depicted is general enough to fit many different approaches, but I think that coming here in the future with some idea, or sending the draft with an analysis of, well, if you go for mechanisms for semantic mapping, or you go for glossaries, using glossaries to cross terms, knowledge graphs, whatever is something that would be helpful in having an idea of which are the tools in the box that we have for this.
Okay. Yeah.
Okay. Thank you very much. So next speaker, please. The next speaker is Cheng Su.
Hello, everyone. So how many minutes do I have? How many minutes do I have? 10 or
7 minutes.
7. Okay. Oh, I will be quick. Hello, everyone. I'm here on behalf of our co-author team, and I will present our draft update on natural digital twin and agentic AI-based architecture for AI-driven network operations. Actually, this is our dashboard version, and we have presented previously at IETF 123, 124, and 125 meetings, respectively, and we have also discussed the topic in NMRG internal meeting March this year. And I should say also thanks to our contributors and reviewers for comments and suggestions from perspective of operators and other technical points. And as you know, we have built GitHub to check all issue and PRs, and everyone is welcome and to report continuous PRs to the report. And a quick status update and what's new for this version. And actually, we did a lot of changes in dashboard. And here I want to highlight 4 points, 4 major points. First, that we shifted from previous multi-agent system to hybrid agentic systems. This is to support the collaborative integration of agent skills like APIs and tools, as well as natural digital twin. Secondly, we streamlined the architecture focus by removing the network element level agent integrity from the core architecture and moving it to appendix for future exploratory. This made our architecture is more clear and more focused on system level or currently software level or controller level. And third is that we strengthened the background and defining the instruction section with comprehensive background context, including natural digital twin, agentic AI, and the ability that AI can bring to network operations. Fourth is we deepened the gap and the challenges, including young adoption and to agentic AI, agent benchmarking, and the ability of agent observability, control, and intervention. So look into the architecture itself, and there are 4 core characteristics in the architecture. The first is a hybrid multi-agent system. This is to feature a single no-span agent at the top, and below it is the multitask agents, and as well as the ordering tools and some other interfaces as well. As required, whatever you want to add it here. Second is that natural digital twin, it can be a deterministic safety sandbox to validate agent decision in a risk-free environment before configure changes or policy is deployed to the real network. As you know, that natural digital twin is also developed in this NMRG research group, and it has reached the broad consensus, and now this is in publication process. And we think that with the joint or convergence with agentic AI, natural digital twin can also play even bigger role in network operation and management. Third is that we enhanced observability and the human loop in the architecture. This is to tackle the AI black box dilemma and to reduce some uncertainty issue or some emergency issue with necessary human intervention. The fourth is knowledge graph. Knowledge graph is the semantic integration. This is to unify high heterogeneous data sources to build complex multi-dimension correlation across our entire network. And we believe that this can help agent to make better decisions and reduce some limitations. Okay, based on the architecture, just on last Saturday and Sunday, we run a hackathon demo on agentic architecture and our observability. You can see that just part of our whole picture, whole architecture. In this hackathon, we are to validate the core components, including agent system and observability functionality in our architecture. And we have choose the root cause analysis scenario, and we can get the traces, metrics, and logs with agent execution, and we use large language model, Q1, and some environment set to, and use LLM as judge to give the comprehensive evaluation result. And this slide shows us our hackathon results. You can see the accuracy is good, and the token cost, the time consumption is also affordable, and we have very good result. And going forward, we can extend the hackathon with some more tools and models involved, like natural tutorial tree and some knowledge graph and some other components used in our architecture. So what's next? First, we are calling the community feedback, and we hope that more experts and viewers can provide more feedback. And we are here to request for research group adoption for this draft. Some reasons. First, we think that this draft is better aligned with current NMRG charter, and this draft is filling critical gap of high-level architecture, showing how agentic AI fits into natural management. This is a strategic direction designated from Office AD, and just hours ago, we have assigned meeting, also assigned meeting, and a lot of topics is related to this topic. So we think that this actual level draft can lay a foundation for some future discussion or researches. That's all for my presentation. Thank you.
Thank you very much. Sorry, Chris, we do not have time because you have still one last presentation. So yes, the first point is very important before moving forward, that people may please provide feedback on mailing list so that we can progress on that.
Okay, thank you.
Thank you.
Chris, maybe you can send the question in the chat. Thank you.
Yeah. So last presenter, Ming-Se.
Okay, everyone. I'm Ming-Se from Joint Lab. The topic I'd like to share is about a gateway for network knowledge graph management. The knowledge graph is a active topic in NMOP, and we can see a lot of discussions on the collaboration between NMOP and the NMRG. So I think this draft provides a useful bridge between the NMOP and the NMRG. Okay, let's start. So the network knowledge graph ecosystem is becoming mature in NMOP, and there are lots of discussions around the architecture, the data unification, like from YARN to KG, and the domain applications like the traffic modeling and incident management. So I think we are moving from the basic concepts to operational domains, but there is still a critical gap. The knowledge graph construction pipeline is ready, but the interaction is still hard. And more specifically, how can users and applications interact with the knowledge graph, but without any knowledge graph operation expertise? So we figure out 2 points. The first is that the operator needs deep knowledge of the underlying graph schema and entity type and query syntax, like C4 or Sparkle, which are specific knowledge graph of querying language. The second is that there is a mismatch between high-level user expectation and the low-level graph operations. So the core challenge we focus in this draft is to translate the high-level requests to low-level operations. And and we give three key requirements. The first is that we need to handle the heterogeneous inputs, and the second is we need to normalize the high-level intent to an intermediate representation. The final one is we need to ensure the security. We propose a three-layer architecture. In the upstream layer, it process input and interactions. In the midstream layer, it translates and resolves the high-level intent to low-level operations. The last layer, the downstream layer, is responsible for storing the fundamental data and knowledge graph. So in the upstream layer, it supports two kinds of inputs. The first is the user input, which is expressed by the natural language. The second one is the application input, which may be represented as a domain-specific language. In the midstream layer, it receives the high-level intent and translates it into the intent catalog and its hidden intents. And in the downstream layer, it stores the network graph and supports some graph operations. Here we give a use case. In this case, an operator may ask specific HTTP traffic attack affecting a specific service. So the operator inputs a natural language query, and we can translate this query into a cipher. And this cipher can be executed on the knowledge graph and synthesize the final results and return it as as a summary represented in a natural language or some structured data and return it to the user. Okay, that's how thank you.
Yeah, thank you for your effective presentation. Thank you very much. So it's the end of an NMRG session. Just on that. So please, yes, also yes to react on mailing list for the particular for the last presentations that we did not have so much time for question. And again, thank you for participating to this session, and see you soon.
In San Francisco.
Or maybe in an interim before.
Yeah.
If you're going, no. It's recorded. It's recorded on YouTube. Please go.
Yeah, no. That's enough.